for chapter 16, 15, like 16, but one less. So last time we got into KF, and a reminder that KF is the equilibrium constant really for complex ions. And complex ions are usually a metal, a lot of times a transition metal in the middle, and they're connected to a bunch of ligands. And as we talked about, ligands are Lewis bases. And that means that they're able to donate a pair of electrons. And they're typically able to donate a pair of electrons to the metal because the metal is positively charged, which means they're actually good Lewis acids because they are really electron deficient. And the Lewis bases have those electrons to donate, so it works really well. So for example, here, our cobalt means that it really has, and they are connected, by the way, through the oxygen in this case, but we'll just draw it like this. Has basically the six waters there attached to it. It still has an overall charge of +2 because water is neutral, and the +2 comes from the cobalt in this case. And water is a really good ligand because it is polar and it has those non-bonding electrons there on the oxygen. And again, that is really what is binding in here. It is really through the oxygen to the metal. In that case, is how they bind. Something known as the coordination number is something we talk about when we deal with complex ions, and we'll see more of it later on. But the coordination number is essentially the number of atoms that are directly attached to the metal in a complex ion situation. So in this case, really all the waters are attaching through the oxygen, even though I didn't kind of draw it that way, but they're all sort of attached through the oxygen. And that means in this case, the coordination number would be 1, 2, 3, 4, 5, and 6. And that would be what the coordination number there would be. In our cobalt with our chloride here, it has basically 4 chlorides attached. Once again, here each chloride is -1, and the cobalt's +2, which is how we get the -2 charge overall, as this guy's really +2, and all these guys are -1s, basically. Here, the coordination number would be 1, 2, 3, and 4. And you may start to think that maybe the coordination number is always the sort of number that we see here. And it's really not, as we'll talk about in a later chapter. There are certain ligands that actually could attach, for example, in more than one place per molecule. So a very common example of that is if you take something like oxalate, which looks like something like this. So if you had an oxalate as a ligand with a metal, it actually has the ability to attach through both of the oxygens there, the single bonded oxygens. And if you had, say, 2 of them, for example, if I could squeeze it in here, maybe go this way, they would bind there and there. And in this case, even though we only have 2 oxalate ions present, the coordination number here would actually be 4 because that's what's referred to as being bidentate. It has the ability to bind twice per molecule, get like a 2-for-1 special on that deal. And even though there's only 2 of the oxalates, each one does it twice, so you get a coordination number of 4. So we'll talk more about that in a later chapter, but again, it's not necessarily always going to be sort of that number that you see down there. It will be if they are what are referred to as being monodentate, which means they bind only one place per molecule. As we also talked about last time, the ligands do come on one at a time, and they do set up an equilibrium for each stepwise case that they come on, and we could add them all together like we did, I think, at the very end last time and get the overall sort of reaction that's happening. You can also figure out the overall K value. Any questions on that there? So let's talk then about calculations involving KF, and they are a little bit different. And they are a little bit different, as we talked about, because they do have a fairly large K value. And because of that, the formation of a complex ion is really favored in that sense. So if we look at a problem like this, we're going to talk about how to kind of solve this. We're going to take 2 moles of copper 2 sulfate, which is really the source of the copper 2 ions, with a liter of 1.2 molar ammonia. We want to know what is the concentration of the copper 2 ions in solution at equilibrium, just the free copper 2 ions that are floating around. We're going to, in this particular example, which is not always the case, but we're just going to assume that everything just remains at 1 liter. So the volume is just going to remain at 1 liter for everybody, just to make the numbers easy. So what we would do is we would want to figure out the concentration of the copper 2, which would come from this guy. And if everything stays at 1 liter, basically it will have a 0.2 molar concentration. And we would want the concentration of ammonia, which obviously comes from ammonia. And again, for keeping everything at 1 liter, in this case, it would be the same number. So we would do an ice table like normal. So this would be 0.2 molar. This would be 1.2 molar. This would be 0. Now, when we do these type of problems, because of the large value of K, we do make a couple assumptions. And one assumption that we make is that we assume that all the metal ion gets used up, because it's basically a one-way street with a K value that's so large. So the assumption here is that all the metal is going to definitely want to combine with those ligands and make this complex ion. So what that means is when we get to the charge in this case, we actually know what it should be, or the change in this case, it should be the mass or the amount of the metal ion, which in this case is 0.2. This would be minus 4 times 0.2. And this would be plus 0.2. Now you may be wondering what that is equivalent to. It's equivalent to if we used x's. So I'll just put this extra c in here. If we did it with x's, this would be minus x, right? This would be minus 4x. This would be plus x. And we already know that x is basically the 0.2. So that again is where we get the 4 from, is basically kind of the same idea. And obviously this would be the same as here. So it's equivalent to doing our x's, except that we kind of already know the x value and the change is happening in this particular case. Any questions on that there? So that means that really we can, I'm just going to kind of put a little line through this one, and then we'll come down here to our equilibrium line. And that means that we're going to have 0 of our copper in this case. We will end up with 1.2 minus 4 times 0.2. That's going to give me 0.4, and we're going to have 0.2. Any questions on this ice table here? Now, the second assumption that we make when we do these type of problems is this: although we do first assume that all the metals should be used up in the complex ion, clearly if we are looking for the concentration of the copper 2 and we zero it out, it's not much of a problem. But this is still an equilibrium, which means even though almost 100% of this copper 2 is going to end up here in this complex ion, it's still a reversible reaction, which means in order for it to be a reversible reaction, it has to go back the other way, even a little bit, right? So it's got to go back the other way at some point. And what the second assumption is, we will actually still have some free metal ions at equilibrium, but the amount that we should have should be very small. So we should have a very small amount of free, in this case, copper ions floating around in the solution, because almost 100% of them should be tied up in that complex ion. So even though we zero out the copper here, we're actually going to go back and solve for it and try to figure out how much is actually there. And we could do this because now we have the equilibrium concentrations. We could use our equilibrium expression, which is, again, our products over our reactants. And a reminder that, again, you don't want to forget, you have to take the NH4, in this case, to the 4th power. We're going to put in our values here, and that would equal our 5 times 10 to the 13 equals 0.2 divided by our copper concentration and our NH3, which is 0.4 to the 4th. We're going to solve for the copper concentration in this case. Mathematically, what happens is those two guys basically switch places. We multiply the copper 2 to the other side, divide by the Kf, and that gives us that the copper 2 concentration will equal 0.2 divided by 5 times 10 to the 13 and our 0.4 to the 4th in that case. So if we do all that, 0.2 divided by 0.4 to the 4th and divided by 5 to the 13, that's going to give us a copper 2 concentration that is freely floating of a whopping 1.6 times 10 to the minus 13 molar. Is that a lot of free copper 2 in the solution? That's like barely nothing there, right? Which is what validates our assumption that the complex ion does want to be formed. Pretty much almost 100% of it ended up in the complex ion. But because, again, it is a reversible reaction, I guess you could call that a little bit of it still free floating in the solution. Any questions on that there? All right. So let's take a look at a couple other kind of variations on these problems here, and we'll take a look at them together since we took the quiz here today. So let's take a look at this next sort of problem and sort of talk about how we could sort of approach this one. We want to calculate the concentration of silver, AgS2O3 minus, AgS2O3 2, 3 minus, and everybody pretty much. When we mix together 150 milliliters of 1 times 10 to the minus 3 silver nitrate with 200 milliliters of 5 molar Na2S2O3. This is a stepwise equilibrium that we got here. So as we talked about, we basically are putting one ligand on at a time, which means, as we talked about, we can get the overall reaction that's happening here by simply adding these together. So if we took these guys and added together, this guy here and this guy here would cancel, and that would give us the silver ion plus a couple of these ligands, S2O3 2 minus, will come on and make our complex ion, AgS2O3 2 3 minus. And the Kf in this case would be found by, what do I do again with those K values? I need to multiply them, right? So we take K1 times K2 in this case. And if we do that, we get 7.4 to the 8 times 3.9 to the 4th. And that's going to give us here, we'll call it 2.9 times 10 to the 13. So this is the overall sort of reaction that's happening after we put on both of the ligands in this particular case. That's our Kf for the overall reaction. But we do have this sort of stepwise fashion, and these steps are going to be really helpful since in this case, we're pretty much looking for like everybody's kind of concentration at equilibrium. So we're looking for really the concentration of everybody. So to start with, we can begin this problem with the overall reaction that's taking place, but we do need to make sure that we get the concentration of everybody correctly once the solutions are mixed. So in this case, we're taking 150 milliliters, right, of silver nitrate, and we're adding it to 200 milliliters of our ligand, and that's going to give us a total volume here, right, of 350 milliliters. So we could do a little M1 V1 equals M2 V2 action on this to get the concentration of silver once it's been mixed together. And obviously the silver nitrate is our source of silver ions. So the concentration of silver when we mix it together would be 150 milliliters times the concentration of the silver nitrate divided by our total volume once we mix it together, which is 350. And that's going to give us an opening concentration here for our silver of, we'll call it here, about 4.29 times 10 to the minus 4 molar. Now, obviously, this guy right here is our source of our ligand. So that is the source of the ligand here. So the concentration of our ligand in this case will be found a similar calculation. We're using 200 milliliters of that guy. Its concentration is 5 molar. And again, it's the same 350 milliliters once we kind of mix them together. So we'll do a 200 times 5 divided by a 350. Going to give us a 2.86 molar. Any questions on, we got those numbers. So these are going to really represent our initial concentrations of both the silver and our ligand and our overall reaction. So since we really need to kind of solve for the concentration of everybody, I'm going to start in this case with the overall reaction. And I think I have it not ahead there. I don't. I got silver and a couple of those guys, right? So I got silver plus a couple of those guys there. Making my complex ion here of AgS2O323. And we do have a KF that we also calculated, and that was 2.9 to the 13. Okay, so I'm going to do my ice table just like we just talked about a second ago. We're going to initially use our concentration of our silver, which was 4.29 times 10 to the minus 4 molar. We're going to use our initial concentration of our ligand, which was 2.86, and we have 0. So once again, because this is a complex ion and a KF type problem, we're going to make our assumption that all of the metal here, which is the silver in this case, should be used up, and that's going to be really our change, kind of like our X in our table. So once again, I'm just going to kind of use the numbers. So this is going to be minus 4.29 times 10 to the minus 4. This will be minus 2 times 4.29 times 10 to the minus 4. A reminder again, you got to take that 2 into account there for the stoichiometry. This will be plus 4.29 times 10 to the minus 4. That means at equilibrium, we will have nothing of that guy. We will have basically 2.86 still, and 4.29 times 10 to the minus 4 in this case. First off, any questions on that? Now, from our very first ice table here, we actually just hit 2 answers that we're looking for. We have found or one of the 2 answers. We found the concentration of S2O32 minus is 2.86 molar. Bless you. We also found here from equilibrium that the concentration of our complex ion is 4.29 times 10 to the minus 4. So we got that from that as well. So our complex ion at equilibrium will be our 4.29 times 10 to the minus 4. So we got that guy kind of taken care of. Now, we do want to find this guy and this guy's concentration. And at this point, you really do have a couple of options that you could do. So since they gave me the stepwise formation of each of these guys, and each of these steps are equilibrium type reactions, I'm going to actually use just the individual steps to figure out the concentrations of everybody else. And we'll talk about the other way you could do it in just a second after we do that. So for example, if I just look at my table at this point, I do have this guy's concentration. I do have this guy's concentration, which means I could actually use step number 2 here to figure out that guy's concentration there, since that's the only thing I don't have. I can't really go into step number 1 yet because I'm missing 2 things, right? The only thing I have out of step 1 is this guy at this point. So I can't really go into step 1 to solve for anything. So I'm going to go into step 2 and use step 2 here to solve for kind of that intermediate guy in the middle. So to do that, what I'm going to do is do my equilibrium expression here for K2, which would be the concentration of our products, which would be our complex ion, divided by our kind of intermediate guy there. and our S2O32 minus. That is going to equal not the Kf for the overall reaction, but it is going to equal the K2 value here. So this equilibrium one, since I'm using that as the equilibrium, and I probably shouldn't have wrote over it. That was, what is that there? It is to the fourth. All right. So that's going to equal, in this case, 3.9 times 10 to the 4. That is also why I am not squaring my S2O32 minus, because in this one, there is no coefficient. Yeah, so I'm not using the overall reaction here. I'm using the second reaction there in the stepwise formation. I have all these numbers, so I could kind of put it in there. 4.29 times 10 to the minus 4 divided by kind of that intermediate, which is what I'm looking for. And then this would be 2.86. Math-wise, once again, these two guys are basically just going to kind of switch places. And that would give me that this guy here would equal 4.29 times 10 to the minus 4 divided by 3.9 times 10 to the 4, and our 2.86. Putting in our numbers here, we will get 4.29 to the minus 4 divided by 3.9 to the 4 divided by 2.86. That's going to give us a 3.8 times 10 to the minus 9 molar as the concentration of this guy here at equilibrium. Any questions on that there? So I now have the concentration of this guy, which was 3.8 times 10 to the minus 9. Now that I have this guy done, all that's left is silver. And what I could do now is actually go to the first reaction here, because now I just solved for this guy, which means the only thing that's missing is the silver now out of the first one. Again, I'm going to use the first reaction here and the equilibrium constant for the first reaction, not using the overall reaction. So if we go into that one, which is our K1 is equal to AgS2O3 minus divided by our silver and our S2O3 2 minus. We again are going to put in our values here using K1. That's going to be 7.4 times 10 to the 8 here is going to equal what we just solved for, which is 3.8 times 10 to the minus 9 divided by our silver, which is what we're looking for, and our 2.86. Once again, I'm using this equation, so that's why there's no squaring again of anything. And then once again, math-wise, we're just going to switch these guys basically. So that will give us a silver concentration in this case of, and my silver concentration should be a large number or a small number? Should be a really small number, as we've been talking about, and 1.8 times 10 to the minus 18 molar, I think would qualify as being small in this case. So in this case, because we were given the stepwise sort of formation, we could use each of the individual steps because they're all equilibrium reactions, and we could solve for each of the things that we were missing. Any questions on that? Yeah.
So is it 0 over 0? It's like approximately.
Where we're talking about here? Yeah, it is. So it's kind of like what we did in the first one where we kind of zeroed out. But again, because it is a equilibrium reaction, some of it has to come back the other way. So you have to have a little bit of free. But in this assumption is because the K value is really large, most of it, almost 100% of it is tied up in that complex ion. So you should always get a really small value for the free metal that's floating around. So if you do this calculation and you see yourself with a really large value for that free floating thing, you definitely did something wrong in terms of the math, because it should end up being really, really small. Okay. Other questions? Okay, so what I was talking about earlier was, I took the approach here where I use each of the steps to figure out sort of the concentrations of everybody. But if you wanted to, you could have just used the overall table and actually started with silver first, like we did in the first problem. So for example, if I'll just show you that here, maybe I'll just get rid of, let's get rid of these guys here. I'll keep the silver there. So let's just say you want to take maybe a different approach and you wanted to figure out, what is the silver off the bat? And you could use the overall reaction. You could do it just like we did in the first example, which is at this point, once we did the first table, we could then have gone back and said, all right, I'm going to call this X and I'm going to solve for my silver concentration first using the overall reaction and the KF. So if I did this, my KF expression in this case would be our complex ion divided by our silver concentration and our ligand. And now because we are using this equation, we do need to square it, and we do need to use the KF that we calculated as well. So if you wanted kind of to go right after the silver after this first table, you could. We again will basically just kind of switch these guys around, and that will give you that the silver in this case would equal our 4.29 times 10 to the minus 4, which is our complex ion, divided by 2.9 times 10 to the 13, and our 2.86, which we would square in this case by putting our numbers in. And if you do all that, you should end up with the exact same number that we had a second ago, which is 1.8 times 10 to the minus 18 molar, which is the exact same number that we got here. So you definitely could still use the overall reaction and hit the silver first. At this point, it would be necessary to then go into probably the first reaction, because if you did that, you would then have this guy's concentration, this guy's concentration, that would then allow you to get to the kind of the intermediate between. So you would still have to dive into probably one of the kind of individual reactions if you kind of took that approach, but it should come out the same. And the nice thing is they're all equilibrium concentrations, so you could just toss them into any of those sort of reactions. Any questions on that there? All right, so this is sort of a stepwise formation. And again, you could add them together, use the overall, but it may require you in a sort of a stepwise, if it's given to you like that, to kind of use the individual reactions to sort of figure out maybe some of the concentrations. Any questions on that there? Okay. So let's take a look at one last sort of variation on a problem like this. What is the molar solubility of silver chloride in 1 molar ammonia solution? So this is actually something that you would do in those qualitative analysis experiments that we talked about a little bit the other day. And this is one of the ways that you actually test for the presence, for example, of silver being there. And ammonia has the ability to basically remove silver from chloride and make this complex ion. So we have two types of reactions happening. We have a KSP reaction, which is our silver chloride going to silver ions and chloride ions. And we have a formation of a complex ion, which is our KF here, where the silver and the ammonia come together to give us this complex ion. So what I'm going to do here is just get our overall sort of equation that's happening here. In this case, as it may seem odd to you right at this moment, the silver ions actually do cancel out. And that leaves us pretty much what it is asking in the question, which is silver chloride plus some ammonia will make this complex ion and our chloride. Now, if I want a K for this one, is it okay to multiply a KSP and a KF together? The answer is it is, because they're just K values, right? Same idea as when you take Ka times Kb to get Kw, right? So they're all equilibrium values. It doesn't really matter what the little symbol is. So we can multiply here our two K values together. And if we do that in this particular case, we will get 1.6 to the minus 10 times 1.5 to the 7. That's a 2.4 to the minus 3. questions on that? Okay, so we're going to do this problem, and clearly at this point, we don't really have a free metal ion floating around. So this is really not necessarily at this point a KF type problem. We're looking for the molar solubility, which means it's more of a KSP type problem, right? So even though we got kind of both things happening, we're actually looking at the solubility here. So that's how we're going to approach this, as more of like a KSP type problem. We're going to take our overall reaction here, which is, again, adding these guys together, there are silver chloride plus our ammonia, making our complex ion. And we got a little bit of chloride passing through as well, with our K value here of 2.4 times 10 to minus 3. So in this case, really the only thing given to us in this reaction is the ammonia. So we basically have 1 molar, and that's the only thing sort of given to us. We don't have anything given to us about these guys, so it's safe to assume it's 0. Although we are interested in silver chloride solubility, it is a solid, which means I'm not going to put any kind of numbers and stuff there, because it should not go into the equilibrium. The change here is going to be like normal. We don't normally have stuff on the left-hand side when we do a KSP, but in this case we will. So we will do the same thing. This can be minus 2s, right, because of the coefficient. S being, again, the molar solubility like we talked about. This will be plus s and plus s. That means that when we get to equilibrium, we will have 1 minus 2s, s, and s. Any questions on the table here? So very similar to a KSP table, except in this case, we actually do have a little bit of something there on the left-hand side. Just like before, we will go into our K expression, which will be our complex ion here, and our chloride divided by our NH3. And once again, we do need to square it in this case. That is going to get us 2.4 times 10 to the minus 3 equals, that's going to be s times s divided by 1 minus 2s squared. Yeah. We're going to solve for s here, and if you look at it, you should hopefully be able to see it is a big old square root action, right? A little perfect square happening there on both sides. So I'm going to try to remember to actually square both sides here. So let's square root it. So if I take square root of the left there, I get 4 I don't know, we'll call it 90 times 10 to the minus 2 equals s over 1 minus 2s, right? So I'm going to multiply this entire thing to the other side, and that's going to give me 4.9 times 10 to the minus 2 minus 9.80 times 10 to the minus 2s equals s. I'm going to bring this guy back to the other side by adding it to it. That will give me 4.90 times 10 to the minus 2 equals 1 plus 9.8 to the minus 2. Going to give me basically 1.098 s. Lastly, we're going to divide this to the other side, right? So we're going to take 4.9 to the minus 2 divided by that. Gonna get us an S, I'll go up on top here, of 4.46 times 10 to the minus 2. That is the molar solubility, right, of silver chloride in ammonia. First off, any questions on that calculation? So basically that would be our 6. If we converted that into grams per liter by using the molar mass of silver chloride, kind of like what we did early on, that's going to give us 143.4 grams per mole. That will get us something like 6.39 grams per liter is the solubility of silver chloride in ammonia. If you remember perhaps the solubility of silver chloride in water, which was one of the earlier type of calculations we did, was something like 0.002 grams per liter. Which one is it more soluble in? It is much more soluble in ammonia, right? I mean, you can't even get like 0.0, it's basically 0.002 in 1,000 milliliters. Here you could do about 6.39 grams in 1,000 milliliters, much more soluble in this ammonia. Why we use ammonia, for example, if you put ammonia, this solid will disappear, and it will not really disappear. It actually gets caught up in this complex ion, and it'll be floating around in a solution. What you typically do is you then throw some nitric acid in there, which gets rid of the ammonia, and that allows the silver and the chloride to come back, and you actually see the solid come back. So it's kind of used in one of those qualitative analysis experiments to kind of pull silver out of the silver chloride. Because of the formation of the complex ion is so favored that if you throw ammonia in there with silver, even though it's tied up already with silver chloride, it's going to go, no, thank you. I'd like to go with the ammonia. There's such a strong sort of attraction, and it's favored by that really large K value, as opposed to obviously the very small K value that we see in the KSP for silver chloride. Any questions on that there? No. All right, that wraps up chapter 15.